Okay, welcome to East Academia. My name is Brian Madena, and my colleague here is Emmanuel Wambua. So today we are going to derive the expression for instantaneous current for a buck chopper with an RLE load, and which is operating in continuous conduction mode, CCCM. Other texts refer to it continuous current conduction mode, CCCM. Okay, so in this case, this is the circuit diagram whereby we have a voltage source, Vs, we have the switch, which is the chopper, and we have the freewheeling diode. So we have a resistor, the R, L, and a back EMF, which is an E. And mostly usually an E usually is like the back EMF that is found in motors. Okay, so basically these are the motors are the types of the load that usually provide such a load. Okay, now today this video in particular is going to deal about the analysis found in mode 1, and in mode 1 we are going to talk about this when the switch is on. The equivalent circuit of this circuit when the switch is on is given as follows, whereby we have the source and we are going to short the switch, okay? And we are going to have VR as the voltage dropped across the resistor, VL as the voltage dropped across the load, the inductor, this is an inductor, and E as the back EMF of the load. Okay, so in short, I can say VR, the current that is flowing here, is given as I out of T. Okay, and this is the expression. We want to obtain the expression of I out of T. So VR is simply given as I out multiplied by R, and VL is given as L di out, okay, it's a function of time, so di out dt. So now, when the switch is on in mode 1, the KVL equation of this one, you're going to have Vs is equals to VR plus VL plus E, which basically this is I out, okay, in time domain, multiplied by R plus L d I out still in time domain plus E. Okay, so now we need to obtain the expressions for I out of T. But first, to achieve that, you see, we cannot decouple this I out with this one until we employ the Laplace transform. Otherwise, you cannot just factor out I out from this derivative. Okay, so that's why the Laplace transform tool or technique is quite important in this analysis. So from this equation, Vs is equals to V out. Now Vs is equals to I out in time domain of R plus L di out still in time domain over dt plus E. We can get the Laplace transform of this equation. So the Laplace transform of this equation, basically, we are going to have the Laplace transform of Vs, which is nothing but Vs over S, isn't it? Then we count the Laplace transform of I out R. This is nothing but I out, now in frequency domain, R, plus now the Laplace transform, L, then the Laplace transform of the derivative, we know it's going to yield S, I out of S, okay, minus the initial conditions, I out are the initial condition, okay, plus E over S. This is over S, similarly this is over S, simply because this is the same as Vs multiplied by 1, and you can get Vs, then Laplace transform of 1, which is going to give us Vs multiplied by 1 over S, which is nothing but Vs over S. Okay, so let it not confuse you. Okay, so having this now, we want to see this is an initial condition. Okay, so we can have a graph, since we are told this is continuous conduction mode. So we can see that this current usually rises when you close the switch, usually rises from I min, okay, and we can assume it rises linearly to a maximum of I max here. So the initial condition, that is at 0, when time is 0, this current has a value of I min. Therefore, we can substitute this I at 0 to be I mean, okay? So therefore, this expression simply becomes Vs over S is equals to I out, now in S domain, R plus L into S I out in S domain minus I mean, okay, plus E over S. Now, since we want to obtain the expression for I out, we have to open the brackets and make I out the subject of the formula as follows. So we can just take, this is Vs over S is equals to I out of S into R plus L S I out of S minus L I mean plus E over S. Okay, so we can take this and this to the other side, so you can take this side. Similarly, that one you can also take the other side of the bracket. So you're going to have Vs over S minus E over S, okay, plus L I mean is equals to I out of S multiplied by into brackets, okay, you have R plus SL, R plus SL. So that way. So this, we can put these under the common denominator. So we have Vs over E over S plus L I mean is equals to I out of S R plus SL. So as to make I out the subject of the formula, we have I out of S. We have to divide. We are going to get is going to be given Vs minus E over S R plus SL. Okay. Plus L, I mean, over R plus SL. Now, to obtain this function, since this function is in frequency domain, okay, to obtain this function in time domain, we have to employ the inverse Laplace transform, okay? And the inverse Laplace transform is given by Laplace inverse of a function in frequency domain, f of s, is equals to f of t. Okay, so this is the definition of the inverse Laplace transform. We want to go to the mathematics behind it. Okay, now, for us to obtain the inverse Laplace transform of this function, we need to make these denominators in a standard form. Okay, so we have to put I of s is equals to Vs over E. Then for this to be in standard, for which we can obtain the inverse Laplace transform, this s must be alone. It must not have any coefficient. Okay? It must have a coefficient of 1. So we can take out L outside. So we'll have SL. And here we're going to have R over L plus S. So this way we can obtain the inverse Laplace transform. Similarly, to this other part of I mean, we have to take out L also. So that we're going to have R over L plus S. Then, as you can see, L and L, these L and L can cancel, okay? And therefore, we can have I out of S is equals to Vs minus E over SL, R over L plus S, okay? Plus I mean over R over L plus S, okay? However, for this, we can get the inverse Laplace transform directly because this is a constant and this is S and this is R over L. So we can get it directly. However, for this other part, we have to employ partial fraction decomposition so as to obtain the inverse Laplace transform of this part. So let me just say that this is part 1. So let us see how we are going to obtain the inverse Laplace transform of part 1 using partial fraction decomposition. So we just say it's Vs minus E, that part, over SL into S plus R over L. Okay, this is the same as A over SL plus B over S plus R over L. Okay, this is the same as Vs minus E into A, then just take this multiply here and here. You're going to get into S plus R over L plus B into SL. Okay, so we can open Vs minus E is given us AS plus RA over L plus B SL. Then we get the coefficient of S together. So let's see, coefficient of S in this case is A plus BL, and the constant term is R over L A. Now coefficient of, so this is the right hand, this is the left hand side. The coefficient of S is 0, and the constant term is Vs over E. On this side, the coefficient of S is A plus BL, and the constant term is R over L. Therefore, you can say A plus BL is equals to 0, and R over LA is equals to Vs minus E. Okay? Therefore, from here, we can say, therefore, A is equals to Vs minus E, okay? Vs minus E multiplied by L over R. Okay, so this is A. Okay, then from here, we can get B. B will be minus, when you take A, it's going to have minus A over L. Okay, now, having given that B is equals to minus A over L, we are going to have minus 1 over L, then the value of A that you obtained was Vs minus E, isn't it? Multiplied by L over R. So you can have such. Okay. So this can go with this one. So we are going to get that the value of B is equals to minus Vs minus E over R. Okay. Therefore now we can come back. Since we've decomposed this into its partial fraction equivalent, we can write now this whole expression of I out of S in terms of its decomposed or its most simplified form. Okay, so we'll have I out of S is given by A over SL, which we have here, and we got the value of A as Vs minus E, so it's Vs minus E, okay, L over R, then divided by SL, so it's going that way, okay, then plus B, so it's going to be plus B. B we know it's Vs minus E over R. Then the denominator there was for B, S plus R over L. Okay, and then we can also have this other side of I mean over S plus R over L. Okay, so in this case, what you can see basically, this L will go with this L. Okay, so that's the first thing we can see. And we can see from these two, Vs minus E over R is common in both this and this one. So we can factor out Vs minus E over R, okay? And for this one, we remain with 1 over S, okay? And this one, we are going to have minus 1 over S plus R over L, okay? Plus, I mean, S plus R over L. Now from here, we can get the inverse Laplace transform easily, because you know the inverse Laplace transform of 1 over S. We can also get the inverse Laplace transform of 1 over S plus R over L, and similarly like this one. Therefore, now, applying the inverse Laplace transform, I out of S now changes and becomes I out of T, okay? So since it's even time domain, let me just put it, have a notation, not the capitalized one, okay? I out of T is going to be given as Vs minus E over R. Then you know the inverse Laplace transform of 1 over S, nothing but 1, minus inverse Laplace transform of 1 over S, this one is nothing but exponential, minus R over L, don't forget that you have a T, okay, plus, I mean, exponential, minus R over L, T, it's minus, okay, positive becomes minus, and also don't forget the T. So therefore, the instantaneous current in mode 1 that when the switch is on, okay, is going to be given as Vs minus E over R, okay, 1 minus R over L T exponential, okay, plus I mean exponential minus R over L T. Okay, other texts you are going to, okay, there are some more notations which are used, okay. Okay, L over R is usually noted as tau. Therefore, R over L can be given as 1 over tau. So we can find other text in mode 1 giving expression as that way. So Vs minus E over R, 1 minus exponential minus T over tau, okay, plus I mean, okay, exponential minus T over tau. So this is the expression for the instantaneous current in mode 1, that is when the switch is on. So thank you for watching this video, and please subscribe to East Academia, share, like, and hit on the bell icon for notifications when you upload any more videos. Thank you.